This video is on section 7.2 notes, estimating a population mean. So we already started in section 7.1 in estimating a population proportion, and today we're going to look at estimating a population mean instead. And you'll find that the processes are very similar, but just a little bit different. So first, we're starting off with a point estimate again, and so here the sample mean which is X bar. So we've worked with this before. Last time we had sample proportions and population proportions, and we hadn't really talked about those before, so we were introducing new variables. In this section, you're going to notice that the variables are recognizable because we've talked about these before. So the sample mean is X bar, and it's the best point estimate or single value estimate of the population mean. Which is mu. Our other estimate is a confidence interval, and this is just going to be a more accurate estimate because it's going to give us a range of values used to estimate the true value of the population parameter. In this case, the parameter that we're looking at is the population mean. So it's going to use the sample mean, X bar, to estimate the population mean, which is mu. So when we were looking with population parameters, population proportions in the last section, we were using the standard normal distribution. We were using the variable z, and this time we're going to use what is called a student t distribution with variable t. So the distribution is based on t, where t is defined as x bar minus mu over the standard deviation divided by the square root of n, where n is the sample size. And if you look at this, this is very similar to the formula for the z-score. The only difference is that when we found the z-score, we typically had x minus x bar as a data point. X was a data point minus x bar was the sample mean. So this is very similar to what we've worked with before. And this is just something that we use. This t distribution is used when you have smaller sample sizes. So these are some things we know about a t distribution. The t distribution has the same general symmetric bell shape as the standard normal distribution. So if you look at the PDF of the notes that's in color, you'll be able to see this a little bit more clearly. But the standard normal distribution is this bell curve that's kind of on top. This bell curve that is the lowest down is with the smallest sample size. The student t distribution that has a sample size of 12, you can see is getting closer to the bell curve, meaning it just has a little bit less variation. So it's approximating that bell curve even better. The t distribution has a mean of 0, just like the normal distribution had a mean of 0 as well. It's just that we have t equals 0 instead of z equals 0 because we're dealing with different variables this time. The standard deviation of the t distribution varies with the sample size but is greater than 1. And this is what's different, is that because we have smaller sample sizes, we have more variation. So you'll notice that when these sample sizes are smaller, n equals 3, you can see that this variation, that this graph is going to be a little bit wider, and then the greater those sample sizes become, the closer and closer they represent a standard normal distribution, which is that last little bullet point there. So this is where we're going to start to feel like, oh, this is similar to what we did in the last section. To construct a confidence interval, you're going to use this formula. So mu is in between the sample mean minus the standard error or the margin of error and the sample mean plus the standard of error or the margin of error. And the margin of error is going to be using the t value instead of the z value, multiplied by the standard deviation over the square root of n. And of course, this is different than what we did last time, but overall the process is going to feel somewhat similar. To interpret the confidence interval, we're still going to write the same sentence. So we're a certain amount % confident that the true population mean lies between two specific values. Okay, so we're going to go ahead and first look at how to find a critical value when we're talking about a t value. So if you looked on Moodle, there is a t distribution table that looks like this. And this is also in the back of your book. So the t-distribution table means that you have to use it, you have to know two things. And one is the confidence level that you have, and then the other thing is the degree of freedom. And the degrees of freedom are just based off how big your sample size is. So if we look at this, if your sample size is n equals 11, then your degrees of freedom, or DF, is just n minus 1, so the degrees of freedom are 10. So you're going to want to be very careful with this, because we are going to use n equals 11 later when we construct our confidence interval, but to be able to find the critical value, or the t value for this specific problem, we're going to use the degrees of freedom. We're going to use 1 less than n, and that would be a place where students could make errors. So there's that. We're also going to look at the value of alpha divided by 2. So if we have a confidence interval of 95%, then we know that alpha is 5%, or 0.05. And we know that's kind of the amount of, almost like what the outliers are. So that means that our alpha over 2 is 0.025. So 0.025 on one tail, 0.025 on the other. So the values that are lower, the values that are higher. So what we're going to do is we're going to look at this. And this part where it says area and one tail, that's something that we'll look at later. So for these particular problems for section 7.2, you're going to specifically be looking at this part right here. So the area and two tails altogether is 0.05. The degree of freedom was 10, so we would go down to 10. And look at 0.05, and that is 2.228. So that would be our critical value for this problem, 2.228. Okay, so for that example, that's all you had to do was find that critical value, but let's go ahead and use that idea for the next problem. So for this example, it says, listed below are the salaries for a random sample of CEOs, Ford, Apple, Coca-Cola, Intel, Boeing, from a recent year. The mean of the sample is 12,898,000, and the standard deviation is 7,719,000. So here are the salaries listed out. Construct a 95% confidence interval estimate for the mean salary of all CEOs. Interpret the confidence interval, and then what does it tell you about the mean salaries? So just like we did with the population proportion, we started off and we would say P is the population proportion of whatever it was we were trying to find. So here we're going to say mu is the population mean of whatever we're trying to find. So the population mean, and it's the salaries for CEOs. So population mean salary of CEOs. All right, then we need to know what the X bar is. So I'm just thinking through the things that were listed in my formula here. So I need to know X bar, and then I need to know my S, and I need to know my square root N, and then to find my critical value, I'm going to need to know the degrees of freedom as well. So I have X bar is in the problem. X bar is 12,898,000. The standard deviation is 7,719,000. The number of the sample size was 5. That means that the degrees of freedom is 4. And then the critical value at alpha divided by 2. So this is a, what did they say? 95% confidence interval. So we're going to look at area and two tails is 0.05 again, so 5%, 0.05. And the degrees of freedom was 4. So 4, 2.776 is my critical number. 2.776. Okay, so I'm going to start with my X bar, 12,898,000. and I'm going to be adding and subtracting to get my upper bound and my lower bound. I've got my critical value, 2.776, times my standard deviation, 7,719,000, divided by the square root of my sample size. So we use the degrees of freedom, n is 4, to find the critical value, but we use the sample size, n is 5, when we plug it into this formula. So just be careful because we are using both of those values. All right, so let's calculate that range of values then. 12,898,000. I'll make it so you can see it. Minus 2.776 times 7,719,000 divided by square root 5. And then I'll do the positive version as well to find the upper bound. Okay, so there's my two values. Okay, and I'm going to put my commas in so I can read those numbers more easily. So we've got 3,315,000, 22,480,000, well, almost 481,000. Okay, so we're going to write the sentence to interpret the confidence interval. So we're going to say we are 95% confident that the true population mean and it's the true population mean salary of CEOs lies between $3,315,132 and 22,480,868. I went ahead and rounded off the decimals since we're talking about millions of dollars. In this problem, they probably would have specified to round to the nearest million, but if they don't specify, then it's okay. My math lab seems to be pretty good about specifying. And in a testing situation, if I didn't specify, then I would accept all sorts of answers. So lies between these values. And then here, what does this tell you about the mean salaries of CEOs? That's the last question there. What does it tell you about the mean salaries of CEOs? The answer here is not much because we don't have good data. So I want to point out what about this data is a problem. The first problem in the data is that they're taking a sample of CEOs, Ford, Apple, Coca-Cola, Intel, and Boeing. Those are all big, widely known companies. So they're not considering the CEO of an independently owned coffee shop down the street. They're not thinking about maybe a local chain. They're thinking about kind of nationally known companies here, which is going to change how large their salaries are. That's going to have a big impact. We also have this outlier here because apparently in a recent year, the CEO of Apple chose to take a salary of $1 for the year. That's certainly not the norm. So this right here is not going to really be an interval. We can do the math. We can find the confidence interval. We can say it. But if our data is not good, then our conclusions aren't going to be good either. So this does not tell us much. Because your conclusion is only as good as the data you collect. So if we wanted to represent all the CEOs like in the United States, this is probably not representative. All right, let's move on to the next example. This says, suppose 40 Chips Ahoy cookies are studied and found to have a mean of 23.95 chocolate chips per cookie and a standard deviation of 2.55 chocolate chips. Construct a 99% confidence interval to estimate the mean number of chocolate chips per cookie, and then interpret the confidence interval. So mu is the population mean number of chocolate chips per cookie. X bar, the sample mean, is 23.95. The standard deviation is 2.55. The sample size was 40 Chips Ahoy cookies, and so the degree of freedom is 39. And we need to find our critical value. So 99% confidence interval. That means when we look for our critical value, we're going to be using a tail, two tails of 1%, 0.01. And we had degree of freedom is 39, so we're going to go pretty far down the table for this one. 39, 2.708. Okay. So we have X bar, and then we have the critical value, 2.708, multiplied by the standard deviation, divided by the square root of the sample size. So 22.858, 25.042, and the interpretation is our sentence. So we are 99% confident that the true population mean number of chocolate chips per cookie is between 22.858 and 25.042 chocolate chips. Okay, it says suppose the data collected. So we know all this data was from a sample of 40 chocolate chips, and we know that we have the sample mean and we have the sample standard deviation. So suppose the data collected in your sample ranged from 19 chocolate chips to 30 chocolate chips, and those numbers are outside of our confidence interval. what do these values say about the validity of your confidence interval? And the answer is nothing. They don't say anything about your confidence interval, because our confidence interval is about the population mean, the population average. We're not going to use average in this class, but you know what I mean when I say that. So this confidence interval is about the population mean or average, not about the individual cookies. So it's okay if the individual cookies have 19 chocolate chips or 30 chocolate chips, because when you find the mean of those cookies, or when you find the average of those cookies, that's what we're actually looking for. So the answer is nothing. Our confidence interval is just as valid as it was before we found out that some of those values for the chocolate chip cookies were smaller or bigger. Nothing. Our confidence interval is about the population mean, not individual cookies. Okay. For this last example, they say listed below are the ages of randomly selected race car drivers. Create a 98% confidence interval estimate for the mean age of all race car drivers and interpret the interval. So if we look at this, this is similar to the previous problems and what the instructions are asking us to do, but it's different from the previous problems, and that they gave us the sample and they didn't give us the values from the sample like they did in the previous problems. They didn't tell us the X-bar, they didn't tell us the standard deviation. They didn't even tell us the value for n, how big the sample size was. So we are going to have to find those different values from the data. So first, I'm going to go ahead and define mu. Mu is the population mean. And let's look at the problem. The population mean ages of race car drivers. And we could calculate the sample mean and the standard deviation by hand, but we don't need to. I'm going to go ahead and use my calculator to find it. There are also ways, if you don't have this calculator, you can use whatever calculator, scientific calculator you're using at home. Should be able to do this as well. You might have to Google the instructions for how to do it. And if you're using, I think it's StatCrunch on my math lab, you should be able to look that up as well. And if you're having trouble with that, just let me know and I'll find some more information for you. So if you're using a TI-84, you're going to click the Stat button. And then where it says edit, you're going to press enter. And we're just going to type all these numbers in. So 32, 29, 27, 32, 38, 45, 33, 32, 52, 33, 33, 29, 41, 23, 25. Okay, and once we have that, we're going to press stat again, and we're going to go over to calculate, and one variable statistics is what we're going to calculate. And I'm just going to keep pressing enter until I get down to calculate. And it's going to give me a list of the things that I need. So X bar, 33.6. I'm using S of X, the standard deviation of X, not sigma. Sigma is the standard deviation if we're talking about a population, which we're not. We're talking about a sample, so I'm using S. 7.7, I'll say. You can count up your number of samples, but it's also listed here for you. There was 15 numbers that we input. That means that our degree of freedom is 14. And now we can find our critical value. So we have a 98% confidence interval, and so that means we're going to be looking at area in two tails is 2.02%. And so we're looking at a degree of freedom of 14. Down here, 2.624. All right, so X bar plus or minus 2.624, standard deviation divided by the square root of the sample size. (33.6) minus 2.624 times 7.7 divided by square root of 15. And then I'll do the upper bound as well. Okay, 28.383. And 38.817. All right, so we are 98% confident that the true population mean age of race car drivers lies between 28.383 and 38.817 years. All right, now one thing to keep in mind is that as we work on section 7.1 and section 7.2, it's going to be really easy for you to know which formula to use because you're in the context of that section. So you'll know in the context of this section to use t-values and to use the formula where the margin of error, let me find it, where the margin of error is defined this way. In the previous section, you knew to use your p hat and q hat and n and z critical values and things like that. But when we get to a testing situation, they're all going to be mixed together. So the really important thing is that when you're doing problems for this section, you're keeping in mind that the problems are saying one thing in particular. And that one thing in particular is you're being asked to estimate the mean. You're being asked to estimate the mean age. You're being asked, let's find it on the previous page, the mean salaries. So this is the part where you know that we're using the t-value and we're using the specific formula that we use today. On the problems from section 7.1, you wouldn't be asked about the mean, you would be asked about the proportion. So those are the things that you should be keeping in mind as you work on these, is that right now it's really easy to pick out exactly which formula to use because you're using the same formula on the whole assignment. But when we throw everything together, we'll want to make sure we're looking for those specific words so that we know which formulas to focus on.